Hi, so this is a quick video on following on from the stuff on AC reactance and impedance. This is about AC LCR resonance. So when you have a circuit with an inductor, capacitor, and a resistor, you get a resonant effect. So just a quick brushing over some ideas that we'll need. If we've got an LCR circuit, so it's got a inductor, capacitor, and resistor in it. The impedance, remember, is the combined effect of all the resistance and the reactance in the circuit, so the total opposition to current flow. And it's defined as just the supply voltage divided by the current, RMS values. And we can draw a phasor for the resistance and capacitor reactance, which is pi over 2 lagging behind resistance, and the inductor reactance, which is pi over 2 ahead of the resistance. And remember, we'd use omega equals 2 pi f to find values for those. And the impedance of the circuit would be the vector sum of all those. We would use the value of xc minus xl in Pythagoras' theorem with resistance to find z would be r squared plus xc minus xl squared, or xl minus xc squared. It doesn't matter which way around that is, because the important thing here is that the impedance Z depends on the difference between the capacitive and inductive reactance, not actually on the values of the reactances themselves, but the difference between the inductive and the capacitive reactance. So if we have a look at some frequency relationships in the circuit, if we start with that same phasor diagram, and we've got our impedance we were just talking about, the important things here are that the inductor reactance is proportional to frequency. If you have a higher frequency, you get a greater rate of change of current. So you get a larger induced back EMF and you get a larger reactance. The capacitor reactance, however, is proportional to 1 over the frequency, is inversely proportional. That's because if the frequency is higher, the capacitor doesn't have as long to charge up, so you don't end up with as much charge build up on the plate, so it doesn't oppose the current flow as greatly. So they have opposite proportionalities. So what we're going to look at is what happens if we look at various frequencies. So if we had our power supply with a variable frequency, and we could look at what happens at various frequencies. So if we start off with looking at what happens at a low frequency. Now at a low frequency, the capacitor reactance is going to be very large, and the inductor reactance is going to be very small. Okay. That means that we're going to end up with, for the inductor, because the angular velocity, the frequency is low, that means we're going to end up with a low inductor reactance. But for the capacitor, because the angular velocity is low, we end up with a high capacitor reactance. And because the capacitor reactance is high and the inductor reactance is low, that means we end up with a large difference between them. Okay, which means we're going to end up with a large impedance. So because the difference between XC and XL is large, we're going to get a large impedance, and the RMS current will be low. Okay. Now, what if we were to look at, so at a very low frequency, we get a low current and a high impedance. But what about high frequency? If we go to high frequencies, we basically get the opposite situation. For the inductor, because the angular velocity is now high, we get a high inductor reactance. And for the capacitor, because we get a high angular velocity, that means the capacitor reactance is low. So because we have a large XL and a small XC, the difference between them is still large, which means we get a large impedance. So the difference between XC and XL is still large, so we still get a large impedance and a low RMS current. So for both low and high frequencies, we end up with low currents. In the middle, somewhere in the middle, we end up with this situation where we get the capacitor and inductor reactances being equal. Okay. At that situation, the difference between XC and XL, so XL minus XC, the difference between them is 0, which means that the impedance of the circuit is actually going to be reduced. It will be as low as it can possibly get. Okay. And at that point, the impedance of the circuit is just going to be equal to the resistance, the minimum possible impedance. and the RMS current is going to be maximum at that frequency, at that particular frequency. So that's kind of that idea of resonance coming up, okay? Resonance is where you have a particular frequency where you get the maximum effect, okay? In this case, the effect is a maximum current. So if we were to look at a graph of the RMS current against frequency, it would look something like this, okay? There'd be a certain point where we'd have a maximum current, and that would occur at a particular frequency, which we refer to as F0, the resonant frequency, okay? So at low frequencies is where the capacitor reactance is much larger than the inductive reactance. So the difference between them is large, and you get a large impedance and a low current, a low RMS current. At high frequencies, it's the other way around. We've got the inductive reactance is much larger than the capacitive reactance. So you still get a large difference between them and a large impedance and a low RMS current. But at that resonant frequency in the middle, you get the point where the capacitive and the inductive reactances are equal. That's the important condition. Okay, that means the difference between them is zero. It means you get the minimum impedance, which is equal to the resistance of the circuit, and you get the maximum RMS current, which in this case will just be equal to the supply voltage divided by resistance. Now we can actually use that condition, XC is being equal to XL, to calculate what the value of the resonant frequency would actually be. So if we start with that condition, XC equals XL, and that's really the key condition for this situation. Now we know XC is 1 over omega C and XL is omega L, so we can just express it in those terms. And we can just multiply everything over onto the right-hand side. So we end up with 1, so we multiply both sides by omega C. So we get 1 equals omega squared LC. Separating it into two terms, we've got omega squared is 1 over LC, so dividing both sides by LC. And then we're going to take the square root, so to get omega, it's 1 over square root LC. Omega can be expressed as 2 pi f. So 2 pi, in this case F0, where F0 is the resonant frequency, is 1 over square root LC, and then dividing by 2 pi, we get this expression where the resonant frequency is 1 over 2 pi times the square root of LC, the inductance times the capacitance. You notice it doesn't depend on the resistance at all, doesn't depend on the supply voltage. The only things that affect the value of the resonant frequency are the inductance and the capacitance. The resistance and the supply voltage will affect what the value of the current is at that frequency, but the value of the frequency itself is determined only by the inductor and the capacitor. So, an example, if we went through a problem. If we have the circuit here, which is a 20 volts RMS 100 hertz with a 1.2 kilo ohm resistor, 1 microfarad capacitor, and a 0.85 Henry inductor, we can go through and calculate the reactances and the impedance for the circuit. Now, this was done in the previous impedance video. I'm not going to go through all the working for that again. If you want to see how those values were calculated, you can go back and check out that video. But we're going to use those. So explain whether the circuit is at, above, or below the resonant frequency. If we start with this, let me just get my pen here. So if we start with question 1, at, above, or below the resonant frequency. Now the important thing here is how do XL and XC compare? Now the first thing to notice is that XC is greater than XL, okay? And remember, XC is high at low frequencies, okay? XC is higher at low frequencies, okay? And also, XL is low at low frequencies, okay? So that suggests that we are, in fact, below the resonant frequency. Okay. If we were to increase the frequency, the capacitive reactance would decrease, so that green vector would get shorter and the inductive one would get longer. So it would be moving towards resonance. Okay. So those are the three that actually tell you about whether we're at resonance or not. Okay, so question 2. Calculate the resonant frequency of the circuit. So in this case, we can just use the formula that we derived on the previous. One over 2 pi square root LC. So if we look at the values that we have in that and substitute them in, so 1 over 2 pi times the square root of L is 0.85, and C is 1.0 times 10 to the negative 6, 1 microfarad, so it's negative 6. Extend that over a little bit. And if we plug all those numbers in and do the calculation, we end up with a value of 172.6, okay, hertz, which actually backs up the fact that for our answer for number 1, where we said that we were below the resonant frequency. We're currently at 100 hertz, and the resonant frequency is 172.6. So yes, we are in fact below the resonant frequency. Okay. Number 3, explain what will happen to the current as the frequency is gradually increased. So as the current increases, okay. Now, initially, sorry, not current is increased, frequency is increased. Get rid of that. We're changing frequency, not current. As the frequency increases, what that means is we are going to be moving, we're going to be getting initially closer to the resonant frequency. That means the impedance of the circuit will be decreasing, so the current will be increasing, okay? Until we reach the resonant frequency, 172.6 hertz, okay? Once we reach that point, also we can calculate what the current is at that point, which would just be the supply voltage divided by the resistance. So it's 20 volts divided by 1,200 ohms, just the resistance, which gives us a current of 0.0167 amps. That would be the value of the current at that frequency, which is the maximum RMS current we could achieve in that circuit. Okay. Now, then, but notice it doesn't say that it stops there, okay? So as frequency increases more, so we've gone beyond 172.6 hertz, we're now getting to the point where the inductive reactance will be larger than the capacitive reactance. So the impedance will now be increasing again, and the current will decrease again, okay? So initially we get this phase where the current will increase until we reach resonance, and if you go beyond resonance, the current will decrease again. Okay, and lastly, calculate the value of the inductor needed to make the circuit resonant at 100 Hertz. So if we wanted the 100 Hertz that it is now, as in the diagram, to be the resonant frequency, what value of inductor would be needed? Okay. There's a couple of ways of doing this, but I think the simplest way is probably just to use that same formula, the resonant frequency formula. 1 over 2 pi square root LC. Okay. And now there's a few ways of doing this calculation. If I multiply both sides by 2 pi, so 2 pi f naught is 1 over square root LC. I'm going to square both sides. 4 pi squared f naught squared is 1 over LC. And then I can rearrange that for L. It's going to be 1 over 4 pi squared f naught squared C. And I can plug in numbers that we know now. 4 pi squared is constant. The frequency is 100 Hertz. And the capacitance is 1 times 10 to the negative 6 Henry. Oh, sorry, not Henry, farads. I need to write that in the formula anyway. I'll just remove that. All right. So that'll give us an inductance of, if we do that calculation, which I didn't actually write down beforehand, so I'll just do that quickly. Is, if I've done that right, 2.53 Henries. Okay, would be the value of the inductance that would be required to make that circuit resonant with a 1 microfarad capacitor at 100 Hertz. Okay, so just a real quick summary on those concepts. At low frequencies, you end up with a high capacitive reactance and a low inductive reactance, which gives you a large impedance. At a high frequency, it's the other way around. You get a high inductive reactance and a low capacitive reactance, and you still get a high impedance of the circuit. But for both high and low frequencies, the difference between XC and XL is large, so you get a large impedance and a low current. We get a graph something like this for current as we vary the frequency. At low frequencies, you get XC is larger than XL, so you get a large difference between them, and at high frequencies, it's the other way around. But in that middle point at the resonant frequency F naught, we get a phasor diagram that looks like this, where XC and XL are equal to each other, which means the difference between them is 0. You get the minimum impedance, which is equal to the resistance in the circuit, and you get the maximum RMS current, which is the supply voltage divided by the resistance. Also at that point, if you were measuring it, you can measure the capacitive voltage and the inductive voltage would be equal to each other, and also the resistive voltage would be equal to the supply voltage at that point, at that frequency. And we can calculate the value of that resonant frequency using the formula that we derived earlier, 1 over 2 pi square root LC. Okay, hope that helps.